and get to work on it, and I'll just make a quick go through this again real quickly. Okay. All right, so when you look at the PowerPoint, again, they introduce the concept of latent heat. Again, the word latent means hidden. All right, and it's hidden because early scientists, early as in, like 400 or 500 years ago when people started studying this stuff. Now, long before that, people noticed when, they lived in Europe where it's a lot colder in the winter than it is here, obviously. Anyhow, they noticed that even on a warm day, the snow didn't melt. It's like if you've ever gone skiing, I think one of you, Michael, went skiing. You notice that even on a warm day, the snow doesn't all melt, even though it's way above freezing. And that's because it takes a lot of heat to turn frozen water into liquid water. It takes even more heat to turn liquid water into steam. So, and that heat that's required to do that overall is called latent heat. And the term for changing it from solid to liquid is called heat of fusion. And the definition or term for the heats required to turn a liquid into a gas is called heat of vaporization. Again, these are old terms, probably, at least 200 or 300-year-old terms, maybe even longer, older. So, so you'll notice, like if you were, again, what I normally do with this is I have a lab where we take a beaker full of ice and we put it on a hot plate, and I put a temperature sensor in there, and we turn the hot plate on high and put an automatic stir in there. So it stirs it up, and you measure the temperature over time as you heat it, and you get a nice graph that looks like, do they have, oh, it's in the book. It's not in the PowerPoint. You'll get a graph that'll look much like this. So we start out, if I were to take the ice right out of a freezer and put it in the beaker and measure it, it would actually be below zero on the centigrade or Celsius scale. Then you heat it up, and you'd notice it would stay at zero for a long time. For several minutes, it would stay at zero, and you'd notice the ice would be melting and the water would be increasing. The liquid water part of the water would be increasing, but the temperature would stay the same. And then about the time, all of the ice is gone, then the temperature would start rising, which is in section C of this graph. Okay, that you're adding heat. Now, remember, over here on the left, down here, we've turned the hot plate on high and we're adding heat the whole time. But even during portion B of this graph, even though we have the hot plate on high and we're adding lots of heat energy to the water or to the ice, the temperature stays the same. And again, we're adding heat, but the temperature doesn't change. So all the heat that's being added is converting the ice or the solid water into liquid water. Then once the ice is all gone and it's all liquid, then the temperature will go up until we reach the boiling point. And then again, the graph will level out and the temperature will stay constant while it's boiling. And again, all the heat that's being added is used to turn the liquid water into steam. And that heat is referred to as heat of vaporization. And we measure it in joules per gram. That's what we're probably going to use most of the time in this course, because I think the numbers are easier to work with. Now, you will see, if you were to look on the internet, you'll see it in joules per kilogram, and you'll see it in joules per mole. whereas a mole is a quantity, kind of like a dozen is 12. A mole is 6.02 times 10 to the 23rd particles. So that's used in chemistry. So anyhow, what we're doing is just simply calculating. Today, we're just calculating how much heat. You're either going to calculate, there's three variables. There's heat, the amount of heat added or the amount of heat lost. And we represent that by the letter Q. We have mass, which we're going to measure in grams, which is represented by the little m in this equation here. And then in the book, in the PowerPoint, it uses the capital L for latent heat, which is, again, the amount of heat you got to put in. All right. So what I'm using and what you'll find if you look on the internet for it is a common way of expressing heat of vaporization is to use or heat of fusion is to use I'm on draw, is to use capital H with a subscript of F or a subscript of V, where capital H with a subscript of F is heat of fusion, and capital H with a subscript of V is heat of vaporization. And notice it takes a whole lot more heat to convert water into steam, which is heat of vaporization, than it does to melt ice into liquid water. Notice it's a whole lot more. All right, so all we're doing, again, we have three variables, as you see here in this equation. And all you're doing, you're going to be given 2 out of the 3 in a problem, and you just solve for the unknown. Okay, heat of fusion, and I'm going to leave these for you to do, and then I'm going to go ahead and work problem 5 here. All right, so problem 5 says 2,083 joules. Okay, that's heat. Or let me get my marker here. Oh, wrong thing. There we go. All right, so this is going to be Q. 5.26 grams, that's going to be M. And we're asked to find the heat of fusion, so that's capital H sub F. So all we do is we start out with this, heat equals mass times heat of fusion. So here's your equation, and we're going to rearrange it. We're going to divide both sides by mass so we can get heat of fusion by itself. So you have 2,083, and that's joules, divided by 26 grams. So 2083 divided by 5.26. So that's 396 joules per gram. All right, questions? Okay, problem 6 is basically the same problem, just different amount of heat. Let's see. And then how much energy you saw, that's just Q. So you're just multiplying this by, now, this is a specific heat problem, actually. This is an MCAT problem. So this one's Q, which is heat, equals mass times specific heat of water times my change in temperature. Now this is just what you did on the last worksheet. So, and specific heat of water is 4.2 joules per gram degrees Celsius. All right, so you just plug those in. That's all you're doing. 125 times 4.2, 5 times your change in temperature. Now here is just you take the 125 and multiply it by the 2260, which again I give you 2260 is the heat of vaporization for water. Just remember, if I'm boiling or condensing, it's heat of vaporization. If I'm melting or solidifying or freezing, then it's heat of fusion. All right. Questions? Is that sufficient there, Gio?
Yeah.
All right. So I'm going to stop recording. You guys got any questions before I stop recording?
No, sir.
All right.